Example I did last time.
Gunman. There was a guy with a gun. Like gunman.
That was a quick response. Something like that happened in Hawaii. It would be cool.
So last time we did is we identified on the real axis those are the roots, and also we identified that let's go to K. Okay. And here the direction of the root loci is in these directions. And so that means when K value increase and the roots, location of the roots will be moving per the arrow sign indicated. And here is the breakaway point. The breakaway point is breakaway points are the repeated roots and for certain value of K. So that's what we did last time. So right now we have done on the real axis, then we try to explore the other ways. And here I didn't follow the orders, but here the first one is, the next one I want to do it is to determine the asymptotes of the root loci. The asymptotes, that means asymptotes, that means the root loci for the value of K, for the very large value of K. Okay, so so here the things is, sorry, let me repeat that again. The asymptote is the root loci for a very large value of S, okay, S. But usually a very large value of S associated with a very large value of K most of the time. Okay, so here we, for I don't know which point, here we're going to find the asymptotes. Okay, this one is here. Okay, so that means here is the asymptote. That means the approximations of root loci as go to very large. Okay, so basically asymptotes is only approximations, but that will give us the certain behavior when help us to draw the root loci at a certain point. So here we do this one. And the first one, because this asymptote is approximation of the root loci when S go to infinity, so which means we're looking for S become very large. So under these situations, and you can see, let me see how to explain this one. We can try is this. The characteristic equations as go to infinity, the characteristic equation can be approx xi can be approximated by this. One plus K, and let me expand that out. So that is the 3 plus 3s squared plus 2s, right? Okay, so this is the original one, and then that can be approximated by this 1 plus k, because in this way k s is going to become very large, and right now we not become, because now we if we want to know the behavior of the characteristic equation when for the large value of s, so pretty much we can ignore the lower order of s, okay? And the best way, the roughest approximations as approaching to infinity, the approximated approximation can be like this: 1 s cubed equal to 0, right? Because when the larger value of s, we can ignore all the lower order term. So this is the roughest approximations. Okay, so under these situations, and we see what happens. So therefore, under these situations, the phase angle criterion will give us is this. Okay, and for this example, we assume k is positive. Okay. So the phase angle is given to this, and basically that is equal to 180 degrees, right? And plus 2L times 180 degrees. And at this moment, we can also write up the magnitude criterion, but the magnitude criterion won't be used here. So here you leave a few line space here. Okay, I'm going to write up something here. And here the magnitude criterion is given by this as 3 and equal to minus 1 over k and 1 over k. This one I'm going to not use today. So for the phase angle here, we can know that the S, the calculation basically is 0 minus 3S would be equal to, here we have 180 degrees, and when L equal to 1, and when L equal to 0 is 180 degrees, when L equal to minus 1, so that is minus 180 degrees, when L equal to 1, that is 6,540 degrees, right? 60 minus 60, 180. Okay. So therefore here we can see the S will be equal to 60 degrees minus 60 degrees and then 180 degrees. So that's a calculation, right? And of course, if you want to keep changing the value of L to other things, and I believe the repeated number will be among the 3. So that reason I guess.
Does the negative not come into account?
Negative here?
In the, on the other side, negative 3.
Oh, yes. And so if you like, you can put a negative here.
Okay.
Yeah. So basically here I divide by minus 3 on this side. But basically minus 180 equal to 180. It really doesn't matter. Okay. So here I only pick up the L. Here basically I pick up L equal to 0, 1, minus 1, and 1. If you want to keep changing the L values for other integers, you should be able to get the numbers that basically repeating among the 3, recycling among the 3. So that reason why I here only pick up the 3. Okay. So that means the angle of the S equal to 60 minus 60 and 180. What that means? You see, if we recall, and here again this is scratch. Okay, so here is the complex plane. If we have any point S here, and if that has a phase angle, basically the phase angle defined by here is 60 degrees. And if we have called it S1, if we have another point called the S2, if that S2 has a phase angle minus 60 degrees, so that is indicated by this one, right? And if we have a phase angle, say S3 here, 180 degrees, so that means S3 is here, S3. Okay, so that is what we know from the traditional complex, the locating the point. And right now we pick up this concept back to here. For this one, we say when S is proportional to infinity. So that means this value is these things. You have to replace by borrowing this concept, and you simply put the S1, 2, 3 to very far away from the origin, not fitting into this scenario. Is that right? Because for this one, right now, keep in mind the value of S is very large. For a very large S, that means is the distance is very far away from the origin. At that point, its angle is 60 degrees. So that means here, let me draw this one at a very far away. At very far away, somehow we know this, we know the trend will be like this, right? Are we okay? Okay, so here let me not draw this one on here because this is a very rough approximation. I just show you the concept. So basically, if we want to draw, then basically here the S1 is at infinity. Okay, the S2 is at infinity. The same thing here is at infinity. Basically, the kind of root loci at infinity will be orientation like this. And we don't know the nearby, the proximity between around the origin, because that is the value when S is small, and that value should be carefully taken care of here. But here we're looking for asymptotes. So here I can tell you, at the very far away, the root loci branch should be in such orientation. Are we okay? So right now again, asymptotes is to help us to know what's going on at the very far away. So that kind of gives us certain idea. So that should be like this. Okay. So basically, you can see this branch, at least this branch fixed on here. That shouldn't change too much. So basically, right now we can expect one branch is here, one branch is here. Okay, and in terms of 60 minus 60 degrees.
Is that why you knew Is that why you knew S2 went down because you just because
I know
here that negative 60.
Because I know here minus 60, and so here I locate the S2 like there.
Well, because what I was saying last class, you had like a minus 45, and you took it from this way.
Not minus 45. 60,
or what?
Whatever the minus 45 from.
Well, I'm talking about last class. You had like a negative angle, and you just took it from the real axis only instead of coming down like that.
Minus 45.
I don't remember what it was. It was, but you took away from 180 last class. That's why I was confused.
I have the same question.
Yes.
Because of what he was saying. We did an example where you had minus 45 degrees, but you made that 135
Oh.
degrees.
Yeah, that's
Okay.
right.
No, the minus 45 degree is about the arctangent. And last time I mentioned that one is trigonometry, arctangent or arcsine cosine. They taking the domain is different from the complex domain. So that reason why last time I asked you, once you do it about the trigonometry, you have to convert your domain from there to here. Okay, because they are taking the different domain. So that is the only point. So basically that is two different functions, trigonometry and complex function. They simply didn't talk to each other directly. So that is the point I made last Friday. That's it. Okay, and now here we only talk about the complex. In the complex, we measure the phase angle from the positive real axis. Okay, and then yeah. So this is the roughest approximations, and this one at least give us certain idea how the branch, how the orientations of the root loci will look like. We can make a little bit better approximation, and that will give us a little bit more precise descriptions about the root loci. And I'm going to do it now, and I'm going to using the result drawn here. So the second approximation is this one. So here's approximation 1. Okay. So approximation 2, which is final approximation. Then 1. Okay, so here again, our original characteristic equations is 1 plus k as 3. Okay, so as go to watch the approximated characteristic equation can be like this. So for the roughest approximation, I simply drop all the lower order terms. And for this one, here it's okay. I keep the first lower order term. And then I drop the remaining. Okay, so here let me do something like this one, equal to 0. And for this case, we can make up a good term is this. I think the better way, a better description is this. For this one, I simply do this one. I just give you the and right now I'm talking is the techniques I'm going to use in the standard root loci drawing of this. We simply look at the first term, and then we, based upon the first term, we make up the things. We basically make up is s plus certain numbers, and because this is a third term, we put into this is a third degree, we put in third degree here. So this is the one approximation. So basically in this approximation is this. We're simply looking for is this. Original, we simply approximate is into this one. Okay, and for this case, if we expand it, we simply compare to find sigma. We simply expand the two sides, and then what we have is 3 plus 3s 2 plus 2s, and this one expanded as 3 plus 3 sigma s2 plus etc. Okay, once we expand it, we simply compare the first two terms. That means we compare this one. So from this case, we can find the sigma equal to 1. And that is the standard approximations here. And this approximation will provide us a better approximation than the first one. Okay. And again, people may argue, why not we just use the first one and then that's it. And this is good. Okay, if you want to use this one, that's good enough. But the people just want to be a little more precise. So that really there's no saying which one is wrong or not. But just in terms of the preciseness, right now I'm talking this one is a little bit more precise. And this is a standard way, to do the approximation. So here I provide you the argument, kind of the reasoning is about the approximation. But from now on, once I talk about this approach, we simply take the standard approach, which means in the future you want to communicate with the people, you better take it. Okay, and you can argue this will be good enough, but people won't accept it because that is kind of well accepted standard. Okay? And here I provide you the different thinking, but here for the learning you pick out the one that people accept it. Okay? Okay, so that means in the test or in the homework, in the future, don't argue with me this one is correct. I won't accept it. Yeah, this one finally is a good one. But you have to know the reason behind, so that reason I start from here. Okay? Good. So let me continue on here. So once we done this one, and then we can see what happened here. So again, so here we have is, so that means s plus 1, 3 equal to minus 1k. So our phase angle criteria will give us is this 1 minus s plus 1 cube equal to minus 1k. So that means 0 minus 3 s plus 1 equal to this one. Basically, it's the same follow-up that one. 180 degrees plus 2L, 180 degrees.
Shouldn't your phase angle on the left side be s plus 1, not 1 over s plus 1?
On the left-hand side,
Yeah.
s plus 1.
Shouldn't be.
Should be.
Well, he means it's not a fraction, right? It would just be the quantity s plus 1 cubed. Is that what you're saying?
Yeah.
Yeah, I think so.
I didn't. So this is a 1 over s1 cube, right?
Yeah, we've already got the angle of 1.
So you've broken it up into the phase angle of 1 minus that second quantity. So it would just be...
Yeah, so here, this angle is 0, right?
Yeah.
Yep.
And then this is...
That would just be...
So we're-
I
Yeah.
see. Sorry, yes. I didn't get that.
Like,
Yes.
yeah, so the one
Like
above
this,
would be
yeah.
wrong too, right?
Yeah, this one, should be this one, right?
Like, yeah, so the step above it, right?
Yes. Thank you. So basically here again, that is follow up from there. So therefore, here we know the s plus 1 will be equal to
60 minus 16.
60 degrees minus 60 degrees and 180 degrees, right? So from here, can you tell? Basically, this tell us is this. Again, let me draw on the complex plane in the real and imaginary axis. Here is the s equal to minus 1. So s plus 1 represent is if we has at any point here is our test point. So here this vector represent is s plus 1, right? The difference between s and this point is defined by s plus 1, right? Do you remember? Okay, so that meaning, so if this is point A, and this one is s, and this vector is called s minus a, right? Okay, so we pick up this one. So from here you can see we can be more precise is this. So the asymptote will be centered at minus 1, and then the range to the infinity, let me using the dash line. So this one, and this one. The dash line represent is the asymptotes the root loci. Here we have 3. And those angles, if we want to define it, that is 60 degrees. And here is the 60 degrees. Okay. So asymptotes give us is the approximated behavior for as approaching to infinity. So here, here we can see when at the very large, and sorry, the blackboard is not, the whiteboard is not good enough. So basically here I can say when as approaching to 0, I can use solid line to approximate. The solid line represent is part of the root loci, and here again that is going here. Okay. And the asymptotes shouldn't be used to describe the local behavior. I mean the local behavior, because the asymptotes are good for in our analysis is only for the big value of S, right? So if we zoom out, then we can tell the root loci have 3 branches and orientation should be like this. Okay.
That's
So-
only if you, never mind.
Okay. And any questions? Okay, so again, here I present you the thinking, and that is from here, but this is not accepted by people because they're too rough. And this is a better approximation. And you might ask me, I know some people might ask me, why you not go to the even finer approximation? That's enough. Because we analyze the asymptote, this should be good enough. And this is easy and good enough. So that's it. Okay. I know people, that really is an argument the people when developing this one. And the reviewers of the original proposed method, they will question why not you, really there's an argument there in the history. So here that the people arguing, then gradually people accept this is the standard. Okay, that's it.